Hello everyone, I'm Paul and today we're solving problem 869, reordered power of 2. This is a medium one and there are at least two ways to solve this. So here I will show you what I think is the most efficient. We are given an integer n and we need to reorder the digits in any order, including the original order, in such a way that the leading digit is not 0 and the resulting number is a power of 2. So we need to return true if we can do this or false otherwise. So for example, if n is 10, this in binary is 1, 0, 1, 0. And in case you don't know how this works, let's say we want to transform this into the base 10 representation. We are going from right to left and each time we are doing 2 to the power of the current position. We start from 0, so first we have 2 to the power of 0, next 2 to the power of 1, 2 to the power of 2 and 2 to the power of 3 in this case. Of course this can continue if this number is larger. Now if we do 2 to the power of 0, which is 1 times 0, the result is 0. 2 to the power of 1 is 2 times 1 is 2. This times 0 is 0, and 2 to the power of 3 is 8 times 1 is 8. Now if we add these values, the result is 10, which is this base 10 representation. Now in case you know, there's a simple pattern we can use to check if a number is a power of 2 or not. For example, this is not a power of 2, and I know this because the digit in the leftmost position is 1 and then we have another 1 here, but for this to be a power of 2 we need a 1 in the leftmost position and then every other digit should be 0. For example, let's say n is 8. This in binary is 1 0 0 0 and we see this exact same pattern for every power of 2. First we have a 1 and then every other number is 0. Now we need to reorder this number and check if the new number has not a leading 0 and it's a power of 2. And the only way in which we can reorder 10 is by taking 0, 1. But here we have a leading 0. This is a power of 2, but given that we have a leading 0, this is not valid. Now there are different ways to solve this. For example, you can use permutations, and with this you can check every possible way to order these digits, and every time we just check this, and if we find that this is true, we just return true, and if we end the loop, we just return false. Now this is fine and this works. I've tried this myself and time complexity for this is big O of digits factorial, because this is usually the time complexity for permutations, and you can use a backtracking approach here. But actually there's a very clever and simple solution, so let me show you how this works. First we can create a frequency map, and we are storing here the frequency for digits in n. Here we see 1 1 and 1 0, so we add a 1 with a count of 1 and 0 with a count of 1 also. And now we will iterate every power of 2. So we are iterating every power of 2, meaning 2 to the power of 0, then 2 to the power of 1, then 2 to the power of 2, and so on. So let's start here. 2 to the power of 0 is 1. And the binary representation for 1 is this. We replace this 0 with 1. So we are building another map with the digits for this number. We'll call this frequency map 2, and here we see number 1, so we put this as a key with a count of 1. And now we're checking if these two maps are equal, and given that they are not equal, we continue with the next power of 2. So this is currently 2 to the power of 0. Now we need to move to 2 to the power of 1. And we have two ways to go from here to here. One is to take the current number, meaning 1, times 2. And this is 2. And the other way in terms of binary is to replace this position with 1. Remember before we had the 1 here, now 1 is here. So now we are iterating this power of 2. So we do the same here, we add these digits to a new frequency map. So we add 2 with a count of 1. And we are checking if this map is equal to this map. In this case, it's not. So now we move to the next power of 2, meaning 2 to the power of 2. This is the same as doing 2 times 2 again, and this is 4. Or we can also take this number and replace this with a 1 at position 2. It's exactly the same. So now we add this to a new map, meaning we have a key with 4 and the count for this is 1. Given that this map is different from this one, we continue with the next power of 2, meaning 2 to the power of 3. So now we are checking number 8, meaning this is as if we had a 1 here. So now we add here 8 with a count of 1. These and these maps are different, so we continue. So next number is 16, next number is 32, next number is 64, and every time we are checking if these two maps are equal, and if at any time we find equal maps, we just return true. And if this number becomes 10 to the power of 9, which is the right bound, and we haven't returned true, we just return false. So when n is 10, we will exceed this right bound and we will just return false. Remember when we were here, this was the first map we were comparing. These maps are not equal because here we have a 0. So with this approach, we are already avoiding deleting 0, we are already considering this part. We just need to check if we find a frequency map for a power of 2 that's equal to the frequency map for the input. If we find this, we return true. If we reach this bound and we don't find it, we return false. So with this in mind, now let's go with the code. The first map is a default dictionary with a default value of 0 for every key. And next we'll say S is n, but we are transforming this into a string. And now for every value in this string, we say map at the current value plus equal 1. So now we have our initial frequency map. Now we are iterating every power of 2. So we start from 2 to the power of 0, which is 1. So current is 1. And now while current is smaller or equal to the right bound, meaning 10 to the power of 9, we say map2 is a default dictionary with a default value of 0 for every key. S2 is current in string format. And now we can say for every value in S2, map2 at x plus equal 1. And if map equals map2, we can just return true right away. Else we continue, we say current times equal 2. So this will go on and on up to this right bound. And if we exceed this and we haven't returned true, we just return false. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Time complexity here will be roughly big O of the amount of digits. And this is because this is 10 to the power of 9 and we have roughly 10 keys in every map. So this is overall time and space complexity. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.